Welcome to Module 7, Privacy Enhancing Technologies. Pets have a reputation problem in both directions. They are hyped as magic by vendors and dismissed as academic by engineers. The truth is more useful. Pets are real tools with real guarantees, real cost, and specific problems they solve. And this module's job is to make you the person in the room who knows which is which. We'll cover differential privacy in the most depth because it's the most deployable, then federated learning, encrypted computation, and synthetic data, closing with a decision guide and a StrideWell application. Why do pets exist? There are three gaps that governance alone can't close. Number one, the anonymization problem. Module 3 showed anonymized datasets falling to singling out, linkage, and inference attacks. Pets replace hopeful de-identification with provable properties. The collaboration problem. Two organizations once join inside, for example, cross-bank fraud signals, multi-hospital research, without either of the hospitals surrendering its data. And lastly, the insight versus exposure problem. You genuinely need population level answers, user strength, telemetry, model training, but holding individual level data creates individual level risk. Now, the honest framing, which I ask you to carry through every vendor conversation. Pets don't make risky data use safe, they make specific, well-defined uses possible with bounded risk. Scope the question first, then pick the technology. Now, the privacy enhancing landscape is in 6 cards. Or I'd like to put them in 6 cards. They are not in 6 cards, but I would like to put them in 6 cards. First, which is differential privacy. With differential privacy, calibrated statistical noise makes any individual presence in a dataset deniable. This is our workhouse and where we'll spend most of the time. Next, you have federated learning. With federated learning, we invert the architecture. The model travels to the data rather than the raw data never leaves its source, which could be a mobile phone or the silo. This is something that's actually used by Google a lot. Homomorphic encryption. With homomorphic encryption, computing is done directly on ciphertext. This is genuinely remarkable, but it's still computational expensive for general workloads, as performing computation directly on encrypted text is very expensive. Next, you have secure multi-party computation. With SMPC, several parties jointly compute a result without any of them seeing the other's input. Next, you have trusted execution environment. This is where hardware enclaves isolate code and data even from the machine's own administrator. Here, you're shifting the trust to the chip vendor. And lastly, synthetic data. This is generated standing data sets which are exactly as private as the mathematics behind them. A caveat we'll unpack. Now, we'll spend 2 slides of depth on differential privacy. Then we'll go through the rest of the privacy enhancing technology concept mentioned in this slide. Starting with differential privacy, which is the headline PET. The promise in one sentence is any result you publish would look almost the same whether or not any single person's data was included. So nothing in the input can be pinned on anyone. Mechanically, that's achieved by adding calibrated statistical noise, enough to hide individuals, little enough to keep the trends true. The dial is epsilon, the privacy budget, where lower epsilon means stronger privacy and noisier answers. So the lower the epsilon, the stronger, the less identifiable your data is, meaning we're adding more noise to that data. And crucially, every query spends budget that never comes back, which makes epsilon governance a question, which makes epsilon a governance question, not just about mathematics or statistics. So someone in your organization has to own that budget the way someone owns spends. And the legal significance of differential privacy, unlike remove the name anonymization, data protection, differential privacy guarantee holds no matter what auxiliary data an attacker brings. It is robust by construction to the linkage attack that broke every famous anonymized dataset we discussed in module 3. Where does data protection ends its keep in production? It generally shines on aggregate statistics and dashboard usage, telemetry. So you find it being used across dashboards, usage, the telemetry, published dataset, and increasingly machine learning training through DPSGD, where with DPSGD noise is added during gradient updates. It struggles where the question is individual level or where population are so tiny, so noise swarms the signal, and under unlimited ad hoc querying because every query spends budget. Now the tooling is real, so differential privacy is currently being used by lots of organizations, and there are several open source projects. A typical example is the OpenDP project. Smart Noise, you have Google differential privacy building blocks, Opacus for PyTorch, or TensorFlow privacy for DP training, and the rest. The pitfalls are organizational more than mathematical. Epsilon quietly cranked up to keep accuracy until the guarantee is decorative. No one owning the budget across teams. Noise dutifully added to data nobody analyzes anyway. The adoption pattern that I've seen that works is one dashboard or one telemetry stream, one named owner for epsilon, and the noise disclosed honestly to whoever consumes the numbers. Next, let's go to federated learning. Federated learning inverts the architecture. Instead of centralizing data to train a model, a copy of that model travels to the data source itself. A global model goes out to the device or data silos. Each trains locally on its own raw data. So only the model updates. So the model gets its update and then goes back to the central system. The server then aggregate them into one improved global model. So here the concept is simple. I'm just gonna see if I can draw on the screen. So let's say we have our model here, and you have device 1. This could be a mobile device. 1, you have device 2, this could be a model device, this could be a mobile device, and then you have a PC here, this is device 3, and then you have, let's say, a different device here. I'm just going to call this device 4. So instead of device 1, 2, and 3 sending their data to the let's say central cloud where the model is trained, I'm just going to call this model. So instead of 1, 2, 3 sending data to this central model, the model actually goes to, or let's say a copy of that model goes to device 1. So you have the model here. You perform the training, you get the data, and then train your model. The same thing again is done for device 2. So model also trained here. Same thing for model 3, model 4. And then once you have your 4 updated versions of models, it then gets the trained models now get sent to your central model, which then compiles everything. So instead of your data source or data point sending raw personal data into the model, they are only sending a trained version of their model and sending that to the central model. Now, a common use case of this is with is in Google keyboards. You can have your own independent research on that and see how Google keyboards uses federated learning in training its model, which it uses for text prediction. So in this concept, as you can see, with this concept, as you can clearly see, data minimization has been used. I'm just going to clear my screen just to keep everything clean. We've expressed data minimization in the architecture of how the model, for example, is trained. Now the fine print, because this is where vendor deck mostly go quiet. Gradient can leak. Reconstruction and membership inference attacks can still recover training data from updates. So serious deployment combine federated learning with secure aggregation. So the server only sees the sum, and often differential privacy noise on the update. Federated learning alone is a starting point, it's not a guarantee. Legally, it's still processing personal data on the device, so lawful basis and transparency obligation doesn't vanish. So because the processing is happening on the user's device, for example, doesn't mean you are not still processing personal data. And the operational cost is real. It is heterogeneous, heterogeneous on devices, stragglers, and debugging a training run. You can't generally you can't directly observe. So this is just one thing to put in mind, that the operational cost as a whole is still very expensive, of course, because you're trying to train a model in a device that you generally don't have access to. The cryptographic end of the pool, honestly labeled. Homomorphic encryption performs arithmetic directly on ciphertext with results that decrypts correctly. This is genuinely practical today for narrow tasks like private lookups and scoring, but still heavy for general workloads, and it is improving every year. Now, next, with secure multi-party computation, it lets several parties jointly compute while input stays secret through secret sharing. Production real for specific joint tasks like private set interactions, which powers privacy preserving, contact matching, and ad measurement, joint statistics, and distributed key management. Then for trusted execution environment, it takes trusted execution environment takes a different bet entirely. A hardware enclave shields code and data from the host machine itself. Broadly available now as a cloud confidential computing, with the caveat that you are relocating trust to the silicon vendor, and the side channel attacks are living research field. My rule of thumb for vendor meetings is that if the pitch says fully homomorphic and real time in the same sentence about general workload, ask for benchmarks and take note of the response that you get. Next, let's talk about synthetic data. This is the pet your executive have already heard of. The test environment and demos without production copies, sharing realistic data structure with partners, augmenting rare classes for model training. Now, the catch here is a generator trained on real people can memorize and replay them. It does so most readily for outliers, exactly the people most at risk. Synthetic describes how the data was produced, not what it guarantees. The fix is generate synthetic data under differential privacy. DP synthetic data inherits provable bounds, then evaluate with membership inference testing rather than just eyeballing through the data, and keep extreme outliers out of the generator's training set. Now connect this to module 5 when we said test environment run or mask or synthetic data. This is the technology that promise leans on a good reason to choose it with your eyes open. We've talked about the 6 privacy enhancing technologies, and next we will look at the best way to choose each of those technologies for the specific problem that you are facing. Now, for typical use case of publishing statistics or dashboard from personal data, differential privacy would be the best for solving such problems. Then for use cases like training on data set that lives on users' devices, a good use case for that is federated learning with secure aggregation, ideally with data protection with differential privacy on the update. Just like I mentioned, this is what Google keyboard Google currently uses for Google keyboards. Now, where you have two parties needing a joint answer and they don't want to share data, let's say you have for fraud prevention, for example, you have two banks who are trying to collaborate on fraud prevention, and they don't want to share data, personal data between themselves. Secure multi-party computation is a very good technology to solve such problems, as the private set it's the private set intersection, with private set and intersection being the everyday example. Then a use case for processing sensitive data on infrastructure you don't fully trust. Of course, this directly we should use confidential computing or trusted environment. So TEEs. TEEs are mostly sold as confidential computing, which is why I refer to it as confidential computing. Then next you have the use case of realistic non-production data. For example, in cases where you want to perform tests on a system before it goes live, so you need to have access to production data. You need to have access to a realistic version of production data. So using synthetic data could easily solve this. And then of course you can use differential privacy on these data if you want real guarantees. A narrow lookup or score on encrypted values. For such use case, homomorphic encryption within its comfort zone is best used. And the line I want you to say, I advise people to say in real meetings is always price the alternatives. Sometimes the right pet is not collecting the data at all, of course. Module 5, minimization, beats every technology on this slide for free. Now let's try applying privacy enhancing technologies to our Stridewell application, and let's see how the upgrade goes. First, we start with trend dashboards. Now we provide, using differential privacy, we now provide city level activity insights with a managed epsilon budget. With this, marketing keeps the dashboard and individuals gain deniability. The coach ML future, the personalization now trains on the device via federated learning with secure aggregation, and the all history training lake, the one we saw in exercise 1, is now retired. For friend matching, private set interaction replaces even the hashed contact uploads. Contact matching now happens with no contact list transferred at all. And lastly, for partner research, use differential privacy with synthetic data. We've come to the end of this module, and just as always, 4 key takeaways that I want you to take. Number 1, pets make specific, well-scoped uses possible with bounded risk. They are not a coat of paint for practices that shouldn't happen, of course. Number 2, differential privacy is the deployable workhorse with a guarantee that survives the linkage attack that breaks everything else, governed by an epsilon budget that someone in your organization must actually owe. Number 3, federated learning moves the model instead of the data, but needs secure aggregation and often differential privacy before the promise holds. Interrogate the fine print always. Number 4, match problem to the equivalent privacy enhancing technology. Price the alternative, and never forget that not collecting the data outperforms every technology we've discussed in this module. Next up is module 8, the frontier. We'll talk about large language models, RAG systems, and privacy governance for the AI that is currently eating everyone's data map. See you there.